Hi everybody, this is Mrs. Harding again. I'm here to walk you through activity 5.1b. It's on simulation. We really only have one learning objective, and it is how to describe a simulation of a scenario to determine the likeliness of a given outcome. So go ahead and get into your OneNote notebook, open up activity 5.1b. At the top, you will see a description of the population of China. It says China has experienced tremendous population growth, and as of 2009, the population of China was roughly 1.32 billion people. So you may have heard that the Chinese government has certain policies about having children. But what this question is going to explore is some different ways to estimate the impact of different policies. So in order to help slow or reduce the population, the Chinese government has a few options. You can see them listed there. The first one, the government could implement the policy and after several years determine if the population has increased, decreased, or stayed the same. So they could actually carry it out and then just see what happens. They could develop a probability model and use it to calculate a theoretical answer regarding population growth, and that's certainly a possibility. You'll talk about different probability models as well. And the third one, this is what we're going to take a look at. It says the government could develop a simulation model and use the results of the simulation to predict the impact on the population. So this is what we're going to talk about today, and I apologize, my screen already is not scrolling, so I've got to jump screens there a little bit. There we go. And in performing a simulation, this is what we're going to take a look at. We're going to figure out what we want to know about the chance process. We're going to go through and plan. You're going to be very explicit about how you're going to carry out the simulation. Some of this may seem a little bit similar to experimental design, where you had to be very explicit about how you were carrying out your procedures. You're going to perform many repetitions of the simulation. So simulations are not something that you just perform one time. Typically, you do many, many trials of it. And then at the end, we're going to draw a conclusion based on the results. So we're going to go through three different scenarios in this activity to demonstrate how to carry out a simulation and how to convey your results and draw a conclusion. The first thing that we're going to do is to take a look at this scenario of the population of China. In number 1, consider the steps above, develop a simulation model using the random digit table. On the last page of this, you can do this with the random digit table. You could do this with your calculator also. Either are acceptable. But we're going to talk through this and figure out specifically what needs to be done, what needs to be described. So what we're going to take a look at is how this policy of being able to have as many children as you want until you have a boy will impact the population. So we're going to look at individual families. So you can see there that there's a description of where you're going to get your random numbers from. It says using the random digit table, start at line 101 and read off single digit numbers. Now, if you remember before from experimental design, you need to be consistent with the number of digits that you're using. So because we're really only looking at boy, girl, we only need 2 different designations there. We can just do single digit numbers. But you want to avoid scenarios where you're using single digits for part of it, double digits for another part. You want to be consistent. You also need to clearly label what represents a boy, what represents a girl. So we're going to read off single digits until you get an odd number. An odd number represents a boy, an even number represents a girl. So what you're keeping track of is the members of the family. So you're looking at different numbers, seeing if it's odd or even. If it is even, if it's a girl, then you're going to get another number for that family. And you're going to keep going until you get a boy. So it says here, after you've done a trial, you're going to count how many digits until a boy is born. So generically, you're counting how many kids are in the family. So you're getting digits until you get a boy that's born, and then you're recording how many children are in the family. And then you're going to repeat this trial several times. Then at the end, what are you going to calculate with your trials? Well, you're going to calculate the average number of children per family. So it's important that you actually state that. Find the average number of children per family. And then in here, it's how you're going to draw your conclusion. If the average is above 2, the population will increase. This should make sense. A family has 2 parents. So if they have more than 2 children, the next generation is increased from the previous generation. If it's less than 2, it will decrease. So the next generation will decrease. If it were to be exactly 2, you would anticipate that the population would stay the same, but that's unlikely to happen. So let's take a look at the simulation that was carried out. So you can see in here, in an example simulation, the number of families after 30 trials that had only 1 child was 15 families. That had only 2 children, was 8 families, and so on. Because remember, for each trial, you're going until you get a boy, and then you're counting the number of children in the family. And so then here at the end, to find the average number of children per family, I'm adding up how many total children there were. There were 15 one-child families. There were 8 two-children families. That's actually 16 kids. 4 three-child families, and then only 1 5-child family. And there were 30 families total, so the average is 1.87 children per family. So according to the results, the average number of children per family is below 2. This implies the population in China would likely decrease under this plan. Okay, go ahead and scroll to the next page. Let's take a look at a different scenario. Question number 2 says, 57 students participated in a lottery for a particularly desirable dorm room that has 3 bedrooms, fireplace, private bath, and in the tower on campus. Most dorm rooms are like this. Don't get your hopes up for that. 20 of the 57 participants were all members of the varsity football team. When all 3 winners turned out to be members of the varsity football team, the other students in the lottery cried foul. Use simulation to determine whether an all-team outcome could reasonably be expected. Okay, so let's take a look at this. There's 57 participants, 20 of them are football players. So let's look here at how we're going to set this up. Apologies, the screen's going to flip again. There we go. So first of all, I'm going to set up that numbers 0, 1 through 20 are going to represent the football players. 21 through 57 are the other students. And if you remember from experimental design, you also have to talk about any numbers that would be excluded. So I'm going to read off 2-digit numbers, and I'm ignoring 0, 0 and 58 through 99. I'm going to read them off until I have 3 different numbers. Remember, we talked about sometimes unique numbers are needed, sometimes unique numbers are not. So these do need to be different numbers. They're unique. And then we're going to repeat this 30 times. So what are we actually keeping track of this time, though? Because last time we were keeping track of the number of children that were in the family. This time what we're curious about is how many times it happens that all 3 students chosen are football players. So after each trial, we're actually just recording a yes or a no. Either yes, they were all 3 football players, or no, they were not. So if you take a look at this, we're going to keep track of the proportion of times all 3 students are football players. This is the value that we're going to calculate at the end. So after each trial, you're just writing yes, they were all football players, or no, they weren't. And then at the very end of the entire simulation, you're going to figure out of 30 simulations, how many times was it that all 3 of them were football players. So I'm going to have you pause the video at this point, and I'd like you to go through this. You can use your calculator to do this, to generate the numbers. You're going to go through 30 different trials. That's sort of the number of trials that we stick with. And I want you to determine your own results to this. Okay, I'm going to show you simulated results that Mr. Bowman came up with. In his results, out of 30 trials, he found that only twice out of those 30 trials, oh, I guess he did 50. Sorry about that, he did 50 trials. So 2 times out of 50 resulted in all 3 students being members of the football team. You would have a percent that's slightly different than that, that's fine. Therefore, based on the simulation, there's only a 4% chance that all 3 dorms would go to football players. So because this is sort of unlikely to happen, we would assume that something kind of unusual is going on. And it's usually at this point that people start to ask, well, what would be an unusual percentage of time? And we're just going to say if something happens less than 5% of the time, or if it's expected to happen less than 5% of the time, we would say that that outcome would be slightly unusual. So there is likely something going on with this scenario. All right, let's take a look at the last example. Now, in a lot of these, you can see the note kind of there at the top. There are ways to calculate these probabilities without doing a simulation and just come up with an analysis of the probability of something happening. And we will talk about that in the next section. But for right now, we're just sticking with the simulations to see how likely or unlikely something is to happen. So if you look at this third scenario, it says Mudlark Airlines has a 15-seater commuter turboprop that is used for short flights. Their data suggests that about 8% of the customers who buy tickets are no-shows. Wanting to avoid empty seats and avoid missing an opportunity to increase revenue, they decide to sell 17 tickets for each flight, even though there's only 15 seats. Ticketed customers who can't be seated on the plane will be accommodated on another flight and will receive a certificate good for a free flight at another time. So we need to design and carry out a simulation to estimate the probability that at least one ticket holder is denied a seat on this plane. All right, so this is a different scenario where they're talking about the percent of time that something happens. It says 8%. Now you guys know that 100% is the most there can be. So if 8% of the time somebody is a no-show, what you can do is you can look at 100 numbers and call the first 8 representing a no-show and the other 92 representing someone that does show up. Keeping in mind that you want to stick with the same number of digits, let's take a look at what's written here on the screen. Let 00 through 07 represent a no-show. That's 8% of 2-digit numbers. That's 8 numbers out of 100. And then numbers 08 through 99 is a passenger that does show up. That is 92% of the numbers. So when you're talking about percentages like that, you want to look at 2-digit numbers 00 to 99 and designate 8% to be those that didn't show up, 92% to be those that did. We're going to read off 17 2-digit numbers for just one trial because they're selling 17 tickets. And you're going to count how many passengers showed up for the flight. And we're going to repeat several trials and keep track of how many passengers are denied a seat. So if you'd like to do this for yourself, go ahead and pause. You can use your calculator and jot down your results after 30 trials. Okay, take a look at the screen. You're going to see Mr. Bowman's results here. So he kept track of passengers that were denied a seat. So 0 passengers denied a seat happened 18 times. 1 passenger denied a seat is 20. 2 passengers, that happened 12 times. So out of this, the probability that at least one ticket holder is denied a seat happened 32 out of 50 of those simulations, which is 64%, which is a fairly high probability that at least one person got denied a seat in that scenario. And then you can also read through the NASCAR example that's on page 305 of your book for an additional example, but that brings us to the end of Activity 5.1b. As always, if you have any questions, please let Mr. Bowman or I know.